Hey students, Professor Nugent here. Let's talk about one more thing from chapter 4. We want to cover the least squares assumptions for prediction, which are different from the least squares assumptions for causal inference. Prediction entails using an estimation sample to estimate a prediction model, then using that model to predict the value of y for an observation not in the estimation sample. And this requires good out-of-sample performance, so we need to lay out some assumptions that we have to satisfy in order to for which we can expect good out-of-sample performance. An example of prediction might be estimating the relationship between test scores and student-to-teacher ratios for Southern California. You would get an OLS estimate of the slope and intercept, and then using that estimate of the slope and intercept for the linear relationship between test scores and the student-to-teacher ratio to predict different test scores in Northern California based on the student-to-teacher ratios for districts in Northern California. We would be carrying out prediction because we are using a regression model based on a sample in Southern California to predict observations in Northern California that are not in our estimation sample. Another example of prediction is time series prediction, where you are predicting economic growth for next quarter. You run a regression to estimate the relationship, for example, between the yield curve and economic growth, and can forecast what the yield curve might be, or inflation expectations, things like this, for next quarter, and then predict economic growth therefrom. So to do this effectively, we really do require good out-of-sample performance. So for prediction, our slope, beta 1, is simply the slope of the population regression line. Alright, so we have to assume that the districts in Northern California and the districts in Southern California are part of the same population, so that we can use the same slope estimated from Southern California to predict the outcome variables for Northern California. The critical least squares assumption for prediction is that the out-of-sample observation for which you want to predict y comes from the same distribution as the data used to estimate the model. And this is going to replace least squares assumption number 1 for causal inference. And again, this is just assuming that the sample from Southern California and the sample from Northern California all belong to the same population, so that they would result in the same or they imply the same population slope, the same population variance, same population characteristics. Then you're going to get good out-of-sample performance. If you have different distributional characteristics between the two samples, then you would have different slopes, different relationships between the two variables, and you would get poor out-of-sample performance. So these are our 3 least squares assumptions for predictions. Number 1, the out-of-sample observation, x OOS out-of-sample, and y OOS is drawn from the same distribution as the estimation sample, xi, yi for I equals 1 through n. And this ensures that the regression line fit using the estimation sample also applies to the out of sample data to be predicted. So we're assuming that they come from the same population, the same distribution. 2 and 3 are the same as least squares assumptions for causal inference. We have independently and identically distributed data. So we're randomly sampling is one way to get to that. And 3, we don't have large outliers. And these are the 3 main assumptions we use for prediction. And that's it for chapter 4. Thanks, folks.